Hello, welcome. So in this episode, we're going to be continuing on the CPU that we've been building, and I would like to get function calls working. So currently, there's no way of building functions, like a library of functions that can be shared and called by different parts of the program. In order to do that, we need to simply allow the program counter here to be written to a register during a kind of jump anyway. So currently what we have is the program counter goes into here. It goes on the L bus. We have it being added in the execute unit. So it gets added to the immediate on the R bus. But we do have a provision in here to put our dval onto the bus directly. So potentially what we can do is change this mux a bit to allow the L val, or L, to go out to the register while the result goes out to form the jump address somehow. I'm not sure how, but we'll figure it out. So I did do some things off camera. One thing you'll notice is there's a lot of wires that are coming in and out between these two circuits, and also between all of these circuits down here in order to form the diagnostic information, or what I've been calling the front panel. The issue with this is every time we add a signal, every time we expand the computer, we need to add more wires and more buses going various different places. And all of this is just for debugging. It's not actually useful for the processor itself. And currently we only have 4 registers implemented, and that's mostly because I don't want to have 16 wires coming in and out just to display the register contents, and only to display the register contents. So yeah, this is just problematic. And it's problematic in the VGA front panel as well, because we have to pass all of these on. And so this is getting huge and unmanageable. And we have this big mess on the left-hand side here. And this is just to take all of those signals and cross the clock domains properly. So you can also see the problem in here with all of these pins that are kind of extra just for debugging. So I have implemented a better way, so I'll just fast forward in time. So this is what happened when I implemented a debug bus. You can see that there's still a few signals that are coming out of here that form part of kind of the user interface, and that's partly because I want to use these signals in our test suite. So these are legitimate inputs and outputs, and likely will be used in the processor, not just for debugging. So that's why they're still coming out. But we can see there's this dB signal. And you can see that up here we've got the dB signal going into the register displays. We've got the dB signal going into these diagnostic displays. And you can see that it can just propagate between these. And you can see it going down here as well. So in here, for example, you can see this is the dB signal coming in and going back out. And we've got just a dB val circuit that pulls something off. And you can see this is what's inside. So this is the minimum circuit that you would need in order to pull a value off of the debug bus. So what is the debug bus? Well, welcome to my GitHub page. So yes, this project is now on GitHub. I haven't formally announced that in a video yet, but it's been up for a little while. And one of the things that you can find is in this docs folder, there is Debug Bus. So I've tried to document it a little bit, and it essentially gives you a rundown of what the signals are inside of the Debug Bus. You've got a 16-bit piece of data. You've got 1 bit indicating whether the data is valid for the specific address. You've got 8 bits of address, and the address just indicates which value we're talking about. And then because I didn't want to have to pass the clock around separately, I bundled the clock into the debug bus. that means that there's just one signal that needs to be passed between all of the debug displays. So if you want to read through and understand how it works, you can read through this document. It's up on my GitHub, and the GitHub link is in the description down below. Very briefly, I can go through some of the ramifications in video form. So obviously there's a lot less pins going between these two components. The VGA component just takes a debug signal, and that's it. We have in here, we've got the debug bus circuit down below. So all of those pins are going somewhere, but they're going into the debug bus. So inside the debug bus itself, it's just taking all of those signals and essentially putting them into a giant mux. So here you can see the giant mux. And I'm using the latest version of digital, which allows you to have these miniature pins, which is really nice. It's just a setting on the pin itself. So this is one of the primary circuits, and we've got another one in here. This one just forms a shadow copy of the registers. So then the registers can be a regular register file, and all this is doing is paying attention to the values that get written into the registers, and it saves a copy of them in a piece of RAM, which will just end up being a bunch of registers within the FPGA. So this allows there to be several registers, and you don't need an extra read port on the register file just for debugging. This actually basically adds an extra read port to the register file, but it's in the debug section. So this could be removed and the processor will still work. So that's the debug bus. I also mentioned in the previous video that I wanted to do a bit of simplification in the execute unit. So I've gone ahead and done that. I've just zeroed out the extra pins for now. So this is add, this is subtract, and then this used to be compare, but compare is not necessary anymore. So I zeroed that out. And this used to be the no op, and technically the no op is not necessary anymore either. So I've zeroed that out. Otherwise, I don't think much changed in here. I believe that's it. Yeah. What do we need to do? Well, I kind of outlined it. We need to somehow get the L bus onto the WR val, which goes into the register file. And I'm debating whether or not to do that in this episode, because it's actually quite straightforward now to add all of the registers that we would possibly need, because we no longer have to worry about sending them straight out. So what we could do is we could just give ourselves 16 registers. And the way to do that is to use a register file. So the reason I didn't do like just the register file component before was I needed the outputs for each of the registers. But now that we've got the debug module containing a shadow copy of each register, there's really no reason to do that. So this can be dramatically simplified. So there's a RA and RB. So RD will go to RA, and it'll also go to RW. Let me zoom in a little. Well, let me grab the pins. These will come straight out. We've got result, which goes on D in. We've got clock, which kind of goes over here. We've got RS, which goes over here. Then we've got RD val, which goes on A. This goes here. And I think that's it. So let's use this new feature. So we can put these together. I wonder if we can do it to all of these. Clocks, I guess, don't support that yet. I'm gonna rename this WR val. And then of course we gotta put our source register in there. And then we've got our write enable over here. Probably just okay, I think that's everything in here. So all of this can disappear, basically. That's a lot easier. So we got to configure our register file, 4 bits and 16. Seems to work. Run all tests. Our tests pass. Awesome. Haven't broken anything yet. So we have 16 registers to play with. So we're going to be basically programming this Mux. And currently it's just used for memory operations, but we're going to be adding in something that's not a memory operation. I wonder if we should just separate this out. I'm thinking we could just pull this out into a separate circuit entirely. Oh, let's do that. Let's call this the write back. And all it really contains is a mux. I wonder if this doesn't belong in here now. Don't think it does, because all this should do is control what we're writing to the register. I'm not even sure we need this part here. Well, yeah, no, we do. What I'm thinking is just do that. And I don't think this should be in here either. All right. No, this part stay. This part disappears. This disappears. And then the mem here is not doing anything. So I'm going to lower the inputs to 2 and get rid of that. I think this is all we actually need in the memory circuit. It's just a bunch of wires connecting everything else up. So I'm not even sure this is necessary, but keep it around for now. Oh, this doesn't need to be up there. Write enable. In goes on the write back, and mem likely will just disappear. Okay. So, where would it be? It's all the way at the bottom, looks like. That's unfortunate pin placement. Wonder if we can, let's pass the RD val and result through, just so we can stick the memory access like right here, and also to get rid of that weird pin placement. So the L bus needs to go down there. I wonder if we can just pass it through here. We can make this small now. Oh, 16. There we go. Let's put L on the top, and then result, and then skip. And for the inputs on this, okay, so we've got L, we've got result, we've got RD val. Oops. Here goes result. That. Call this our Mux. I don't think I need to do the T suffix anymore because it's going to the key. Okay, I think that's good enough for now. So we've now got this Mux. We need to actually have an output for it. And I should add it here. So, okay. Okay. All right. I think this should sort of work. Right. There we go. Okay. So we need to update the microcode now. We have result, L, D, and RD val, and result is the default. Let's call it WM for result or write mux. That's 0/9, I guess. L M data eval. Okay, so most of the time we want to write the result, but occasionally we want to do these things. So in the case of memory operations, we want to write either memdata in the case of a load, right? Yeah, we're loading from memory, so we want to write that to the register. In the case of a store, we want to write, well, we actually don't want to write at all. So actually, we don't need art_eval on that mux, come to think of it, because we were using that to make sure that the register contents didn't change. Okay, that's good to know. That'll simplify some things. Okay, so, and then the other option is writing the L value. So I think this is correct, and we don't have the mem bit anymore. So actually that'll move everything down. 6, 7, 8. So we have the ability to put the L bus on the value that we'll be writing to the register file. So, okay. Mem has disappeared. Yeah, guess that's it. Yeah. I wonder if we should keep the mem signal, because that would indicate a memory cycle. Let's keep it for now. We can simplify that and remove it later. So that was here, I think. No, it was here. Yeah, I'll remove that later if it's definitely not needed, but I have some plans for how to support slower memory, and so that signal might need to be re-added at that point. So if we implement slower memory and we don't need this, we can remove it then. So yeah, I think that's everything. Let's jump failed. A bunch of things failed. So our jump instruction is broken. Why would that be? Did we break the microcode? Jump. Oh, actually, we need to write a register here. Jump. Okay, so jump is setting the program counter to 1. Oh. Interesting. Setting it to the L bus. Why would that be? 0. Well, while we're here, we can put call in here. I believe this is 1. Another one of those should work. Okay, stall is down. There's our jump. Right is 0. Jump 1. Right access that. So then result should be 9. It is. Huh? Oh, I see it. Do you see it? It's right there. We're pulling the value off the L bus. Whoops. That's not proper. That's an easy fix. That explains a lot. 9. Yes. And we have 9. Sweet. This should not error now. Error is being skipped. Excellent. And we're halting. Yay. Okay. Our test should pass. And they do. Yay. All right. That was a bit annoying to find. Okay. So we have a call instruction here. Let's, oh, and we have no way of returning. This is broken, and that's what we need in order to return. How do we fix that? Well, let's make a little program here. Now our return address is going to be R0. So this is the instruction that's not going to work. And that's going to be basically our return instruction. So I'm going to put an error halt after this. And I'm going to put an error here too, just in case. And this is technically not in the function anymore because it should be returned. Okay. Actually, we got to add this to our make file. Okay. So we don't have a display for this, but it's calling for, and so that adds 4 to the program counter, and R0 should contain, well, 1, really. And it does. And then we move move 5 into R1. And then this should be our jump instruction. What? So this. 1110, and then our op. So here's our jump R0. It's putting the program counter on L, and then the contents of R0 on R, and then it's adding, and we don't want to add in that case. I am not entirely sure how we're going to get around that. I have an idea. Okay, so we've got our encodings here. Currently we have this space down here, and 2 of these instructions I'm not planning on implementing because they can be implemented a different way. Not is just XORing with -1, and neg is XORing with -1 and then adding 1. So both of those can be done without needing another register. So yeah, if it takes 2 instructions, that's fine. So why don't we put the return instruction in here? I think that would make a lot of sense. So it's 0, 0, 1, and then we've got 2 bits. So 0, 0, 1, 1, 0. 0, 0, 1, 1, 0. Okay, let's do that. Okay, and then in the microcode, so what control signals do we need? We want to basically be the same as a move instruction, but we're moving to the program counter. So it's a move jump. I think that'll work. Okay, so we've got our no-op. We've got our call, the no-op after the call, and then we are moving 5 into R1. And then we move 1 into PC. So PC should become 1. It does. That seems to have worked. It's skipping the error now. And it's halting properly. Yay! So we have function calls and we can return. Awesome. I just had a thought. If I add in the call, then at least I can show something in the thumbnail. Where was that? I think it's just after jump, right? There we go. We have our call, and I'm curious if the other one works. Yep, jump PC R0. Yep, perfect. So, thank you very much for watching. I hope you have a great day. Bye.